All right, so today's notes and homework. So first off, the question is like, what is a polynomial? Because that's what this section is. If we look at the basis of this word, we have the word poly, which means many, and we have, you don't see it, but you have monomial. A monomial means one. An example of a mathematics monomial would be like 4x or 3 or 7x to the second, something like that. But you take many monomials and you put them together. So polynomial literally means many monomials, or is the sum of more than one monomial. That's all it is, sum of monomials. And you put them together and you get a new function. When you talk about polynomials, you have certain things like the leading term, what we call the power factor and stuff like that. So let me give you an example of a polynomial. And we're going to put it out of order. Negative 5x to the fifth plus 3x to the second minus 7x to the eighth. If I can type. Now, there's an example of polynomial. It is not in standard form. In standard form, you put the highest exponent first. So in the standard form would be negative 7x to the eighth minus 5x to the fifth plus 3x squared. All right, now the leading term in standard form is called a power function. And the power function controls what we call end behavior. Sometimes it's called long run behavior, but we call it end behavior in Tennessee. It controls end behavior. So we'll go over end behavior again. You have x to the even. An example of x to the even might be something like x to the second or x to the fourth. And notice it's a positive x to the even. Maybe x to the eighth is an example. And x to the even is going to start high and stay high. Most of you already have this memorized. There's a handful of you that do not, but most of you already have this memorized. Let me get my stylus here. There she is, but x to the even starts high and stays high. And the verbal descriptions is something a couple of y'all have been lacking. But as we run left, as x approaches negative infinity, the y value approaches positive infinity. And as x runs to the right, as x approaches positive infinity, the y value also approaches infinity. Now you have negative x to the even. An example of negative x to the even might be something like negative 3x to the fourth or negative 3x to the 10th, something like that. A negative x to the even is going to start low and finish low. And the end behavior is going to change just a little bit because now, as x runs left towards negative infinity, the y value falls to infinity. And as x runs right to infinity, the y value also falls to negative infinity. X to the odd, we're just looking at odd exponents. It'd be something like x or x cubed or x to the seventh. They always start low and they always end high. So as x approaches negative infinity, the y value also falls to negative infinity. And as x approaches positive infinity, the y value approaches infinity. And lastly, there's negative x to the odd. This would be like negative 2x to the seventh or negative 3x to the fifth. The negative symbol introduces a reflection, so we start high and we end low. So as x approaches negative infinity, the y value approaches positive infinity. And as x approaches infinity, the y value falls forever to negative infinity. All right, there's your notes for that. Of course, I didn't talk about degree. Degree is the highest exponent. Like this guy right here is an 8th degree polynomial. And the degree is also found from that leading term in standard form. All right, so I got 2 examples for you for your notes. You're supposed to rewrite these things in standard form, find their degree, and such forth. So in STD form, this guy, this negative 7x to the 8th, is the biggest thing up there, followed by the 9x cubed, followed by negative 4x squared, and followed by 3x. She is of degree 8, also an 8th degree. The leading coefficient is negative 7. Now, when you put these two together, that gives you the drawing of the end behavior. This is a negative x to the even. She will start low and she will finish low. Oddly enough, the next one's also an 8th degree. In standard form, we got to put the 18x to the 8th first. Boy, somebody messed up these notes. Plus 12x to the 5th, minus 4x plus 7. Also an 8th degree. That comes again, for those of you who just aren't sure what's going on in life, right there. Leading coefficient is 18. So we're looking at a positive x to the even. And positive x to the even starts high, ends high. Easy peasy, lemon squeezy. All right, more of your notes. Using factored forms, make up a function, trial and error, verify with your TI-84 Desmos, write the function, show me a rough graph. So on number 1, we have a cubic function with 1 x-intercept. And I talked about Desmos. Oops. Be nice if I was online, wouldn't it? So a cubic function with 1, if you just make some x-intercepts up, 3 of them, you'd have a cubic function, right? But I only want 1 x-intercept. So how do I take like the first thing and I raise it to, and I give it 1 x-intercept? I raise it to the 3rd power, and that makes it a cubic function. So there she is, x minus 3 cubed. Now, this is not a hard thing. Just make some stuff up and play around, learn something, explore, all right? So I made up a function, f of x equals x minus 3 cubed. And that's going to be right 3, and it's going to have end behavior about, think about that end behavior, x to the odd. It's going to start low and finish high. That's how it works. Start low, finish high. A cubic function with 2 x-intercepts. And it has to be a cubic. So I'm going to make up something with 2 x-intercepts. But that's a quadratic, isn't it? I fix that by taking one of the x-intercepts and making it a square. And then I have a drawing. Notice how it starts low, ends high. If I make it negative, the reflection happens. Start high, ends low, but it doesn't change my x-intercepts. So negative x minus 3, x plus 1 squared is what I went with. And that is a cubic function. Because if we do some near math, we'd have x times x squared. And my power function is negative x cubed, which is high to low, which is exactly what Desmos said this thing looked like. So this one had x-intercepts at negative 3. Oops, I have a typo somewhere. That was supposed to be a negative symbol, wasn't it? It has intercepts at positive 3 and negative 1. All right, so plus 1 means we have an x-intercept at negative 1, minus 3 at positive 3. And I made mine start high. This one has to happen twice. Notice the touch. Rose, came back, fell down forever. And notice that that was a big deal. That was an x plus 1 squared. So x was negative 1. We touched the x-axis. Has to do with the even idea. Even things touch the x-axis. Notice that this is an odd. We cross the x-axis. All right, a little more notes. A cubic function with 3 x-intercepts. Might give myself some more room here. So if I want to have 3 x-intercepts, I can delete that square, and I'm just introduce something else. I'm going to make this one positive so that it starts low and ends high. And there she is. X minus 3, x plus 1, x minus 4. We did a little near math, x times x times x. The power function is simply x cubed, which means we're going to start low and we're going to end high. We have an x-intercept at 3, we have an x-intercept at negative 1, and we have an x-intercept at negative 4. It's going to come in, it's going to cross, curve up, cross, curve down, and shoot up like that. A quartic function. Quartic function is a 4th degree. And I'm just going to make up something else. I'm even going to put out like a negative number up front. If I'm a 4th degree, I need to have 4 distinct. If I'm a 4th degree with 4 x-intercepts, I need 4 distinct x-intercepts. Hey, the last one kind of funny, just x. This one is kind of funny. This is literally x is 0. All right, so I cross at positive 1. I cross at negative 2. I cross at positive 3. And I cross at 0. And it was negative 3. The power function is negative 3x to the 4th. So I start low and I end low. I come in from negative infinity. I cross, I cross, I cross. And I get the letter M. 4th degrees often look like W's or M's. That's for you to do. Here we have our notes, our average rate of change. We have a formula for that. The average rate of change is just another way of doing slope, but the formula is f of b minus f of a, sitting pretty, over b minus a. Now in the first example, I'm going to let you use your TI-84's graphing ability to assist. So off to y equals. Feel free to play along, you know. That's what the graph looks like. It ain't pretty, is it? There's a whole lot more going on. It's not so much the graphing ability as it is the table. Second table. So when x is negative 2, arrow up, I have a negative 12, don't I? F of b is negative 12. Sorry, f of a is negative 12, a and b, until I hadn't woken up. When x is 8, what do I have? I have 8,088. Wow. All right, so plug into your formula. The average rate of change here is 8,088 minus a negative 12. Sitting pretty over 8 minus a negative 2. You should be able to do this in your head. That's, of course, I'm pretty tired, but that's going to be 8,088 plus 12, which is 8,100. And that's sitting over 8 take away negative 2, which is 10. And we divide out the 0 there. We get 810. So on average, as we move 1 unit from left to right, we increase by 810 units. And on this one, we're supposed to do it by hand. So we have to plug that 6 in. I say by hand, we're still going to be pushing buttons in the calculator. I am anyways. I don't know why I'm hitting zoom here. Enter. Negative 15,112. All right, find f of a by doing the same thing, but with a negative 1. This one I think I can do in my head. Because a negative 1 to the 5th is still negative 1. A negative 1 squared is 1. So I have 2 plus 12 plus 8, which is 21. And now I hit this formula right here. Negative 15,112 minus 21, sitting pretty over 6 minus a negative 1. Bottom 7. We'd have negative 1591 up top. I feel like that's right. 12, borrow 9 more, yeah. And does that reduce? It's got a chance. You're dividing an odd by an odd. Apparently it does not. Surprised at that. And you know what? That's because I'm wrong. That was a negative, take away another negative. Those grow negatively. I made a sign mistake. Who would have thought? I need to add 21, so it's negative 15. Negative 15,143. So I need to add the 21. 33. I need sleep. Try this one. Nope. I think I'm about half done now. Using your TI-84, identify the y-intercepts, the x-intercepts, and any local maxes and mins. So you get to use your TI-84 on this. Definitely play along. At least on one of them. We'll see what you do. This is a negative 16x to the 6. If you're thinking like I am, it's going to start low and end low. What happens in the middle? Nobody knows unless you make tables. Or it's something nice that factors, and this is probably not. Zoom 6. It should have a y-intercept at 2. And it does. The y-intercept's going to be right here, which is at 2. If you look at the table, the y-intercept happens when x is 0, so it's right there. It's 0, 2. To find an x-intercept, remember you let y equal 0. So we're going to put a 0 in y2 and use our intersect function. Let's see here, second trace 5. These are not going to be pretty x-intercepts. Remember I said it would start low and end low? I'm pretty confident the graph is done. So I got negative 0.7516. That happened when y was 0. And there's a second one. Get your cursor close. Since there's only a y1 and y2, press enter 3 times. 0.5886. Local maxes and mins. This thing only has one thing. It's right there. It actually has an absolute max. We can find it by going to second trace 4 for maximum. Notice it says maximum. And I'm going to take my cursor and I'm going to move it to the left of the maximum because it's asking for a left boundary. Press enter. To the right of the maximum. Enter. Enter for a guess. There she is, 0.4236, comma, 3.2219. And we're going to do the same thing on the next one. Notice that this is an x to the odd. It's going to start low and end high. And behavior is kind of a big deal. At least it is to me. Which means it should be by default a big deal to you. Your y-intercept is going to be at -3. And you can see it on the graph right there. Don't forget that it's 0, -3, not -3. Your x-intercept, I kind of closed that real quick, but it looked like it only had 1. Something really close to 1, isn't it? Second trace 5 for intersect. Get close. Enter, enter, enter. 0.7623. Now, you talk about local maxes and local mins. If a function looked like this would be a local max. And this would be a local min. The graph you have in front of you, it just looks like that. It has no local max or min. So, bad examples. All right. I'm going to save 7 because I'm kind of low on time. I'm at work right now, but I have to go pick up a car in Indiana today, so I can't be here. These are notes. Allie has a piece of construction paper that she wants to use to make an open rectangular prism, a box with no top. She will cut a square with side lengths x from each corner of the paper so the length and the width is decreased by 2x as shown in the diagram. And first off, we're going to write a function that models the volume of the rectangular prism. Volume of a prism or a box is length, width, height. And this is 11 minus 2x here for the length. The width is 8, take away 2x. And she is x units tall. So one of the lengths is literally x, one of them is 8 minus 2x, and one of them is 11 minus 2x. Now it says graph the function, identify a reasonable domain. Now here's what I know. Volume has to be bigger than 0. So each of these factors have to be bigger than 0. X has to be bigger than 0. 8 minus 2x has to be bigger than 0. And 11 minus 2x has to be bigger than 0. So if I solve, negative 2x is greater than negative 8, divide by a negative, x has to be less than 4. If I solve this one, 11 greater than 2x, x has to be less than 5/2. Now here's your two winners, this one and this one. X is a number stuck between 0 and 4. You like your interval notation 0 to 4. Now let's take a look at the graph and see if what I'm saying on paper justifies that. We had one length of x, we had another one is 8 minus 2x, and we had another one at 11 minus 2x. And you'll see I just found your x-intercepts to some degree. There's one at 0, 4, 5/2, or 11/2. I don't know why I changed it to 5/2, that's 11/2. And those are your x-intercepts. And I only want the stuff that's above the graph. Now, why doesn't this one make sense? Let's say that x was 6, because that's bigger than 11/2. If x was 6, this piece wouldn't exist, nor would this piece. What's happening here is you have a negative times a negative, which makes a positive. This thing comes in from there, goes up for a while, goes down, shoots up. The only stuff I care about is this right here. This little piece right here is extraneous data. Anything from that area makes no sense. But this is the real stuff. Down here, this would be negative volume. So you can kind of see what I was saying about being stuck between 0 and 4 makes sense. All right, what do the x-intercepts of the graph mean? Those are the locations where the volume is 0. Which means there is no box. Value wants to maximize the volume of the box, which is the side length of squares that should be cut from each corner of the piece of construction paper. So I'm going to look up, I don't know, 200 units, which I think is plenty. And this point right here, where my cursor is going to be the absolute maximum volume of this box. Second, trace 4 for maximum. Take my cursor, get her to the left of the maximum, press enter. Get to the right of the maximum, press enter, enter for guess. The x value that maximizes it is 1.5252. And the max volume happens to be y. And it is 60.0126. Oh, sorry, 60.0125. Yeah, 60.0126. 60.0126. And that would be in cubic units. All right, there you go, Allie. There's your box. Right, live, laugh, love on it. And everything else is for you. And you've got some time. Again, the notes are half the grade. So enjoy that. Hopefully you have some free time now. You should. It was only a 30-minute video. You should still have, 14 minutes or so.